Swayam Prabha. Digital India. Educated India.
Hello, welcome to NPTEL NOC, an introductory course on Point-Set-Topology Part-II. Today we shall start a new topic, topology of manifolds. Manifolds are central objects in the study of topology. Though the idea of a manifold can be traced back to Riemann in his work on the so-called Riemann surfaces. Of course, Riemann didn't call them Riemann surfaces, obviously. A formal definition of this manifold may be attributed to Hermann Weyl. Its study is a must in any kind of higher mathematics and things that use higher mathematics like theoretical physics and so on. Our aim here is quite modest, dealing with only very few salient topological aspects of topological manifolds as compared to deeper studies such as additional structures with PL manifolds, smooth manifolds, Lie groups and so on and so forth, complex manifolds and so on. So we are just taking topological manifolds which in some sense encompass all such special things. Okay, so it is so general, therefore it is going to be somewhat weak. Statements are somewhat weak here. Okay, but they will be available for all those studies. So both ways they are good in that way. All right. First, we shall study some topological aspects of manifolds in general. We shall then take up the classification of one-dimensional manifolds. Next, we shall merely outline the classification of compact two-dimensional manifolds. This is aimed at motivating you people to study other topological areas like algebraic topology and so on. Okay, especially the NPTEL course on algebraic topology. There are two courses. So this will be a motivation, as well as this entire course will be a very good preparation for those courses finally. Okay, so today module 55, definitions and examples of manifolds. Fix an integer n, take a non-empty topological space. By an n-dimensional chart for x, we mean a pair u, psi consisting of an open neighborhood u of some point x inside x and a homeomorphism psi from u to Rn. U is an open subset of x. U to Rn onto an open subset of Rn. Often when I say homeomorphism, it is not necessarily onto here, but onto some open subset. You take that subspace topology, there it is a homeomorphism. Okay, here I have specifically mentioned that the image is open inside Rn. That is very important here. U is open inside x does not mean that psi u is open inside Rn. So that has to be hypothesis here. Okay, that is a condition here. Now once you have defined a chart, I am going to define an atlas Okay, these are borrowed from geography. I think all these things goes to Gauss. Okay, so by an atlas we mean a collection of uj, psi j of charts. Okay, charts, collection of charts. What is the condition? The union of all these domains of the charts must be the whole of X. If there is an atlas for X, then we say X is locally Euclidean. In other words, the chart gives you local Euclideanness of capital X at the point X. If it happens at all the points, then it is called locally Euclidean. X itself is locally Euclidean. A chart u comma psi is called a chart at x naught if you can choose this psi to be such that psi of x naught is 0. This is a very special definition I have cooked up so that I don't have to keep on saying that psi of x naught is 0. At x naught means the function is such that x naught is chosen as the origin, going to the origin here. So also we keep writing psi as psi 1, psi 2, psi n. These are the n coordinate functions because psi is taking values inside Rn. So these n component functions, coordinate component functions psi, these are called local coordinate functions for x at the point x. The local coordinates, remember, not defined on the whole of x, they are defined in a neighborhood of this little x or x naught. Okay. For n greater than or equal to 1, okay, I think n capital N is the same thing as n greater than or equal to 1 here, integer. X be a topological space. We say X is topological manifold of dimension n if it is locally Euclidean in the above sense. Okay, that is, there is an atlas consisting of n dimensional charts. Now this n is occurring there also, same thing, same n. The second and third condition is just ordinary topological condition. This is Hausdorff space and second countable. Okay, so these two extra conditions we put because we don't want to deal with non-Hausdorff spaces. We don't want to deal with non-second countable spaces because then we cannot do any analysis. Any countable discrete space is a zero-dimensional space, zero-dimensional manifold. Don't confuse this one with the definition of zero dimensionality for a topological space which is just a separable metric space. Okay, so this is a manifold definition, we have got it. It is a subset of that. Okay, but we insist that it is countable discrete space here. We don't want to take all arbitrary zero-dimensional spaces, second countable separable metric spaces, which we have defined as zero-dimensional, namely satisfying S2. Okay, so that is the difference here. It will satisfy S2 because it is a discrete space, but converse may not be true. That is why we have to be careful here. So this will cover now n equal to 0 case also. Okay, and n equal to -1 is covered if you want, namely when X is empty set. Now that is allowed. We would like to include the empty space also as a topological manifold. However, there is no good way of assigning a dimension to it. Some authors prefer it to be dimension -1, just like in our dimension theory, and some others put it as -infinity. Indeed, there are theories, in the topology of manifolds itself, where it is better to treat the empty set as having any dimension whatsoever you want. It is like zero polynomial. Okay, zero polynomial, usually people don't define the degree. Okay, but it is better to keep 0 polynomial having any degree it wants, depending upon the context. Observe that once a chart view psi is, exists at a point, x naught belonging to x means what now? Psi of x naught is 0. Then we can choose another chart v comma phi at x naught such that this phi of v is the whole of Rn. In fact, this is some point going to some open subset of Rn, may not be the whole of Rn. You can take a smaller set like this and you have to change side, you have to change phi of v is the whole of Rn. Therefore, you could have assumed right in the beginning that all the charts have this property, but that is not always convenient. Okay, it's better to have as many of them. The moment you fix up things, there may be less chance. That's all. Okay, by composing with a translation, we can assume first of all psi of x naught is 0, and then we can choose R positive such that an open ball of radius r is contained inside this open subset around 0, right? And then take v to be psi inverse of br0. Then what happens? Psi itself is a homeomorphism from v to br0. But now br0 to the whole of Rn, you have lots of homeomorphisms. You compose with them. For example, you can take x going to x by r square minus x square. This is a homeomorphism, very nice homeomorphism from br0. Okay, ball of radius r, open ball of radius r centered at 0 goes to the whole of Rn. For an atlas, it is necessary to assume that the integer n is the same for all the charts. Okay, don't change the n there. Of course, if x is connected, you are free to change also, but you have to use a certain theorem which you have seen, namely Brouwer's invariance of domain. Okay, namely Rn is not homeomorphic to Rn. So you will not have much chance there, because once different n's are used, the n that occurs will be a locally constant function on x, but x is connected. Therefore, a locally constant function has to be constant. So this n and m etc. can't occur, only one of them will occur. Okay, so that is a minor point. It is better to assume that you don't have like a line and a disjoint union with a point. Such things we don't call it as a manifold. That's all. Okay, because line can be parameterized by open subsets inside R, right? It itself is a single parameterization is there. Single point, you have to take it as a discrete space. Okay, single discrete space, it is a countable discrete space. Therefore, it is 0 dimensional. So don't mix up such different dimension. That's all it says. All right. Thus, the dimension of the chart at a point becomes locally constant, and a locally constant function on a connected space is a constant function. Okay. For a topological space that is locally Euclidean, second countable, and Hausdorff. Okay. Condition the second countability. Why we choose that one? Is equivalent to many others. What is the meaning of that? Under locally Euclidean, say locally Euclidean implies, remember, it is what? It is locally compact, it is locally convex, and so on, right? So a lot of things. In any case, it will be locally Euclidean means a lot of things. Second countability condition is equivalent to many others such as metrizability, paracompactness plus connectedness. Okay, all these things are equivalent. So we find second countability is the most suitable for our purpose. Okay, easy to understand. The Urizone's metrization theorem that we have done tells you that every second countable T3 space is metrizable. Locally compact Hausdorff spaces are T3 spaces. Therefore, they are metrizable. So I could have put metrizability, and then I can conclude that it is second countable. Okay, since manifolds are locally Euclidean, they are locally compact and hence regular. Okay, metrizability is not enough, separability you have to put. Okay, therefore we obtain every manifold is metrizable. In particular, every manifold is paracompact because we have proved metrizable spaces are paracompact. Okay, so to sum up, started with locally Euclidean plus Hausdorff, then you can just put that it is metrizable and separable, then it will be second countable. Or you can just say paracompactness and connectedness, that is also good enough. So all these things are going one into the other. In particular, given any open cover U of a manifold X, using local compactness, we can first take a refinement V of U. See, I am now talking about this paracompactness. When you have paracompact, you have partition affinity also. I want to see something more here in the case of manifolds. So what is that? Start with a manifold and an open cover. Take a refinement V which consists of open sets whose closures are compact. So here I am using local compactness. Such sets are called relatively compact. See, we have never used it. Say, so many times we have used U such that U bar is compact, right? There is terminology for relatively compact, means that. You could have used that terminology. Then we can get a partition of unity theta I subordinate to this V. Subordinate means what? Support of theta I closure. The support of theta I itself is actually closure of all the points wherein theta I is not 0. So that support of theta I is a closed set already. That should be contained inside members of one of the members of V. Okay, but members of V are such that their closures are compact. Therefore, these theta i's have compact support. Okay, so that is what automatically this will imply that it will be subordinate to U also, and the extra property support of theta i's are all compact. So this is not true in general for paracompact spaces. Okay, you have a partition of unity which is subordinate to U, that's all. But I have extra hypothesis here, namely support of theta i's are compact also. This will be quite useful now. I am going to use this one. So let us see some examples now. If you have studied some differentiable manifolds inside Rn, like a circle, sphere, parabolas, ellipses, ellipsoid, and so on, they are all manifolds. Okay, take some time to see that, right? But I am not going to do that. I am going to do only simpler examples. Okay, so that is your calculus course, full of manifolds there. The boundary of the unit square as a subspace of R2, okay, is a topological one manifold. Even simpler, if you take a triangle, any triangle, okay, the boundary of that triangle consisting of 3 sides, that will be a topological one manifold. you may have learnt that this is not a smooth manifold. Inside R2 it is not a smooth manifold because triangles have corners, the squares have corners and so on. Because of the corner points cause problems, right? If you don't know that, don't worry. They are all topological manifolds. Why? Because suppose you have a corner like this, okay, what you can do? You can, this line segment union this line segment is homeomorphic to this line segment, right? All that you have to do is turn this vertical thing, make it horizontal like this. Okay, you can write down your own, use cos theta sin theta formula and write down the homeomorphism from this union. In fact, you can write a homeomorphism from this first quadrant to the entire thing also. Okay, so this is a nice illustration. This picture tells you how to handle corners. See here, point here, locally they are lines, open line segment. They are no problem. But here, what is it? You have to just straighten it out to get a homeomorphism into the interval. That's all. All right. Now let X be the union of two axes in R2, X axis or Y axis, X axis and Y axis. You can draw it anywhere. You don't have to take the axis itself. If U is any connected neighborhood of 0, 0, how does it look like? If you throw away 0 from U, it will have 4 connected components. Okay. Therefore, you can see that such an open neighborhood of U, namely neighborhood U of this point 0, 0 inside X, X is the union of axes, right, cannot be homeomorphic to an open interval. Okay. So, cannot have any chart covering 0, 0 and hence fails to be a topological manifold. All right. So, if at all, you should have a homeomorphism to R, because everywhere else except this point 0, 0, the intersection point, everywhere else you have neighborhoods which are homeomorphic to open intervals, but at that point you don't have. Now I will give you some very specific example here which violates the Hausdorffness. We have put Hausdorffness forcibly. Suppose Hausdorffness is a consequence, then you don't have to put that one. No, it is not a consequence. That means what? I am going to construct a locally Euclidean, locally one-dimensional Euclidean space, which is actually, you can take countable, so it can second countable also, or you can cut it off and make it compact also, no problem, but it will not be Hausdorff. Okay, let us see how. Let X be the set of all real numbers, okay, that is the real line, together with one extra point that we shall denote by 0 twiddle. We shall make X into a topological space as follows. The tau is a collection of all subsets A of X of the form A is B union C, where B is allowed to be empty or an open subset of R in the usual topology. So, empty set is also an open subset of R in the usual topology. But I want to emphasize this fact that it could be just empty. Why writing a B union C? Okay, that is the first part. What about C? And C is either empty, C could be also empty, or C has the property, C is a subset, both B and C are subsets of X, right? So, first part says it is a subset of R itself. That means 0 twiddle is not there. Now, the second part also says it is empty, or 0 may be there, you see 0 twiddle may be there. So, you intersect it with R. That means what? You are throwing away 0 twiddle. But now you take union with 0, throw away 0 twiddle and put back this 0. that is now a neighborhood of 0 inside R. Is that clear? What is the relation between 0 and 0 twiddle? If you just ignore the other one, then the rest of them looks like a real line. If you ignore one of them, both of them are there and they are so close to each other, you cannot separate them. The moment you take a neighborhood, that neighborhood will intersect. See, this neighborhood is some open subset. You throw away that point and put back this neighborhood. It's the other way around. Put back this point, 0 twiddle. That will become a neighborhood of 0 twiddle, and vice versa. Okay, therefore 0 and 0 twiddle cannot be separated by open sets, but they are different points. So this is why it's called line with a double origin. You can throw away many points like this, at least several discrete set of points. For each integer you can double them. That will be a funny space, but it will be locally Euclidean the same way. You can not only one point, you can put any finitely many points also like this. The same property. This is 0 twiddle, 0 twiddle, twiddle, 0 prime and so on. You can index them by another set and so on. So this is just the idea, but you can expand it to very large, very complicated space also. Without the hypothesis Hausdorffness, you will get strange spaces, okay, which we don't want to deal with. They don't occur naturally. It is only a consequence of our definition, the deficiency of our definition. Therefore, we have to put Hausdorffness. Okay, so I again describe this. Notice that the above rule describes all neighborhoods of 0 twiddle. You may say first part describes all neighborhoods of 0, but this one describes all the neighborhoods of 0 twiddle also. Namely, take any neighborhood u of 0, okay, throw away 0 and add the singleton, add the 0 twiddle singleton. So that is your C here inside that one. If you take the intersection, 0 twiddle goes away and 0 comes back here. So that is a property. Alright. So to verify that this is a topology, all that you have to do is intersection, finite intersection, countability, that we will leave it to you. Okay. Let us go ahead now. So this is one which we have studied a couple of days back, the long line, using our well-ordered order topology and so on. Okay, we know that long line is locally Euclidean. Okay, it is Hausdorff also. What is it not? It is not second countable. It is not even first countable if you allow the omega, but omega is not allowed inside the long line. So it is first countable, but it is not second countable. So therefore long lines are not treated as manifolds. Okay, so that is an example. So we should have sanctity for why these conditions are there. Okay, we don't want to discuss long line on which you can't do much analysis. Another type of non-example is obtained by taking disjoint union of manifolds of different dimensions. This I already dealt with, like taking an open arc and a singleton point outside, or a line and a disjoint plane. Those things are not allowed. We don't want to consider. So for example, such spaces are there if you go to algebraic geometry, okay, wherein even larger class of objects are studied. Let us consider some examples of manifolds that do not occur naturally as subspaces of Rn. So far, our examples were all subspaces of Rn and counterexamples were not subspaces of Rn, right? Now let us see something which does not occur naturally as subspaces, but they are manifolds. So this is the one very important example, projective space. The foremost one in the n-dimensional real projective space, which we have introduced in part 1. But let me recall only a few aspects of this. I hope you know it. If you don't know, you can read it from there and so on. So some few of them which perhaps are not there now, it is there, it is here now. So first of all, the Pn is said, what is the definition of Pn? Pn is the quotient of the unit sphere Sn inside Rn plus 1 by the antipodal action. What does that mean? X and minus x are identified. Antipodal action means x goes to minus x. So look at the equivalence classes. I can denote them by bracket x and take the quotient map Q from Sn to Pn to be Qx equal to this bracket x. So put the quotient topology. That is the space. So space is defined over. Automatically, this is a surjective map find. It's a quotient map. So it's continuous. If Sn is compact, therefore Pn will be compact. Okay. So we have to see why it is locally Euclidean and Hausdorff. After that, we are happy because it's compact Hausdorff space already, so it will be second countable also. All right. Since Sn is compact, Pn is compact. Now, given any x belonging to S, consider V to be the set of all points in Sn such that the distance of that point are less than square root of 2 from x. So take the root 2 ball inside Rn plus 1, intersect with Sn, that will be an open subset of Sn. Right? Now if you take x going to minus x, y going to minus y, okay, under that this open subset will go to a disjoint open subset. Right? Therefore, if you restrict the map Q to V, that will be a 1-1 map. Right? So this Q is actually homeomorphic to this V is actually homeomorphic to Q inside that. Okay, QV will be homeomorphic because this is a neighborhood which is, you can see that it is homeomorphic to an open ball inside Rn. I have taken open ball inside Rn plus 1 intersecting with Sn. So that is homeomorphic. So that is the nice neighborhood. So this will give you local description that every point inside Pn has a neighborhood which is homeomorphic to an open subset of Rn. Okay. Indeed, this also tells you that the space is Hausdorff now. Because what you can do is, let me see, I will tell you something more. Take x and y distinct points. What does it mean? Plus minus x is not equal to plus minus y. If x is not equal to y, these brackets, their classes are different, means plus minus x is not. So you have 4 different points. Now you take arbitrary 4 different points are there, right? You take the least distance between all of them, call that epsilon, take epsilon balls around plus minus x, epsilon ball around plus minus y. All these 4 balls will be disjoint. Okay. First of all, this epsilon small, minus of this plus minus that, those will be disjoint. From y also they are different because that is the way I have chosen this epsilon. Alright, so that will show that when you take their images, this B epsilon image Q of that and Q of this, they will be neighborhoods of square x, I mean this bracket x and bracket y, so they will be disjoint. So I have included some exercises here. Show that a manifold is connected if and only if it is path connected. So this is exercise, very easy exercise. But there is another exercise here. This is not very central. Even if you don't understand this, it's okay for some time. Okay. So why this actually obsession with Hausdorffness and local Euclideanness? Okay. So if you look at the cofinite topology on R, that is not a Hausdorff space. Okay. But is it locally Euclidean? You can ask. Right. So there are, we have given a space like locally Euclidean which is not Hausdorff. Suppose Hausdorffness, does it imply local Euclidean? There are many such cases. So like that you can go on asking questions. So that is why I am discussing this one. You can take a look at it, and if you have difficulties you can come back to us. Okay. So today let us stop here. Next time we shall introduce a larger class of manifolds which are called manifolds with boundary. Thank you.